Alright, geometric sequences and series. Just like with arithmetic stuff, sequence has commas, series has plus signs. And just like arithmetic sequences, we're going to have a couple of formulas that are useful to us. The sum formula and the explicit term formula. And we're going to add a third thing, which is the sum of an infinite geometric series. Meaning, if you had infinity terms and added them all up, do you get a sum or not? Turns out there's an important caveat, and that's that the terms have to be really, get smaller and smaller. Anyway, we'll get to that at the end of this video. First of all, let's look at the explicit formula, shall we? So just like the arithmetic sequence, you could find the 10th term, the 15th term, or whatever. All you had to know was the first term and then the common difference. Well, in this one, all you have to know is the first term and the common ratio. Now, the common ratio, r, is just whatever you're multiplying by to get from term to term. So let's take a look, find the 8th term. So find t sub 8. The first term looks like it's 1. And then our r, what is our r? Well, it looks like we're multiplying by 3 and then multiplying by 3, so our r is 3. The n minus 1, we're just going to pluck that n. See how this n and this n? Same n. So if I put an 8 down here, that means I need an 8 up here for n, but then there's a minus 1 right there. So I got 1 times 3 to the 7th, and we're going to need calculators in this one. In the geometric sequences, you pretty much always need a calculator because these do get ugly. So we're going to do 3 and then the caret symbol, 7. And you get 2187. Pretty exciting stuff. First term is 4, sixth term is 128. What's the common ratio? Well, we can solve this the same way we solved for the common difference in the previous video. Once again, I'm going to use this explicit formula again. What am I going to put on the left though? I'm going to use t sub 6 because I know the sixth term, so that means I'll be able to plug it in. So first I'll just write my formula. T sub 6 is going to equal t sub 1 times r. The n minus 1 and n is 6, so that's 6 minus 1. Alright, so t to the 6, let's plug in stuff. 128 is equal t sub 1, first term is 4, times r to the 7th. Divide both sides by 4, I get r to the 7th equals, let's see, 128, 32. Now at this point, sorry, r to the 5th. Whew, that's crazy. 6 minus 1 is 5, not 7. Alright, so r to the 5th equals 32. Let's rewrite that. R to the 5th equals 32. So what is r? I happen to know off the top of my head that 2 to the 5th is 32. So r equals 2. The way you could do it on a calculator, though, is to get rid of an r to the 5th, you need to take the 5th root. Like, square root symbol with a 5 next to it. These can be kind of hard to find in a calculator, but it's usually in the math menu. Another way to do it is just raise it to the 1/5 power. So if I raise both sides to the 1/5 power, which is the same thing as a 5th root, you can see this 1/5 will cancel that 5, so we've just got r on the left. And then 32 to the 1/5 power, I can just plug that into a calculator. Just be careful with parentheses. So what you want to type into a calculator is 32, and then the little exponent symbol. And at this point, you'll need a parenthesis, because you want 1 divided by 5 to be your power. You don't want to do 32 to the first power, then divide all that by 5. You want the power to be 1/5, so it's got to be in parentheses. But if you plug this in, you should get 2. All right, so those are kind of easier problems. They can also get a little bit harder. So what are geometric means? Well, they're just terms. So basically what they're saying is, hey, find 3 terms between 16 and 1 in a geometric sequence. So I'm like, all right, that's easy. 16 blank, blank, blank for my 3 missing terms, and then 1 will be the last number. Now, whenever I see a problem like this, usually they have kind of like round numbers they're working with. So there's a good chance that r is something silly like 1/3 or 1/2 or 1/4. I know it has to be a fraction because I'm going from 16 to smaller numbers. I'm going to be either dividing by a number, if you will, or multiplying by a fraction. So if I multiply by 1/2, I'll get 16 times 1 is 1/2 is 8, times 1/2 is 4, times 1/2 is 2, times 1/2 is 1, and it worked out. So if r equals 1/2, I just get 8, and then 4, and then 2, and then 1. Another way to work it would have been to just use our explicit formula. So if we know that t sub 5, since I have the first term and I have the 5th term, so if I counted these 1, 2, 3, 4, 5, so this is the 5th term. So t sub 5 equals t sub 1 times r to the 5 minus 1, which is 4. So if I just plug in the numbers I know, t sub 5 is 1. 16 times r to the 4th. So that means r to the 4th equals 1 over 16. Now at this point, I could type this in. I could raise both sides to the power of 1/4 to get a 4th root, and I would get some crazy decimal. Actually, maybe I wouldn't. I'd get 0.5. So r equals 0.5. At that point, you'd want to realize, you know what? That's 1/2. So and then once you have your r, once again, you would just plug it in and hopscotch in order to get your missing terms. Because they asked for not the r, they asked for the missing terms. So you actually do have to find the missing terms. All right, crazy calculator example. I'm guessing there's decimals going to be involved if I introduce it with that. All right, so 4th term of a geometric sequence is 3, and the 14th is 59. So what's annoying about this problem is that they're not giving the first term. They're asking for the first term. All right, so the 4th term of geometric sequence is 3, and the 14th is 59. We want the first term. So it looks like I'm going to need r. It's really important to have r if you want to find the first term. Because if I had r, and I had like the 4th term, I could just plug all that in and solve for r the way I did on the previous page. But the problem here is I don't have r, so what I have to do is figure out r by saying, you know what? To get from, I have the 4th term, term number 4 is 3, and then term number 14 is 59. So that means that I had to jump, terms 5, 6, 7, 8, 9, 10, 11, 12, and 13 are all between here. That means I had to jump 10 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get here. So I multiplied by r 10 times to get from 3 to 59. But since it's geometric, that means that r, so that doesn't mean that 10r equals that difference. That means that if I I took 3, the first term, and I had to multiply by r to the 10th in order to get 59. Because 14 times 4 is 10. So at this point I can solve for r. Divide both sides by 3, so I get, and then raise it to the 1/10 power. R to 10 equals 59 over 3. And then I have to raise that to the 1/10 or the 0.1. Ugh. So 59, this is why it's a calculator problem. So I'm going to have to do parenthesis. Okay. 59 divided by 3, parenthesis, raised to the power of 0.1. And that's going to equal 1.347. So r equals 1.347. So now I can go back to the original formula here. And just, I could pick t sub 4. So t sub 4 equals t sub 1 times the r I just got, 1.347, to the 4 minus 1, which is 3. And this is cool because I know some stuff here. I know that t sub 4 is 3. I know that t sub 1, that's what I'm solving for. And then my 1.347 to the 3rd. So at this point, I've got to take 3 and divide it by 1.347 to the 3rd. So 3 divided by, since I still have my 1.347, I'm just going to hit second and then negative sign, which is ANS, to the 3rd power. I get 1.227. So t sub 1 equals 1.227. Pretty nasty. A lot of times I want you to round the nearest 100th or 10th or something, but you get the idea. The point is it's nasty, but they can ask us for the first term if they give us some combinations of later terms. So this is one of the ones you just want to practice with quite a bit. All right, sum formula. This is pretty straightforward to use. It looks kind of like weird, and I don't see where they got this thing. The sum in an arithmetic sequence, it kind of makes sense if you look at it, sort of where the formula came from. This one I have no idea, but it works. I've tried it. All right, so find the sum of the first 10 terms. So what we're looking for is s sub 10. That's what this n means. So we're just going to plug in stuff. So first of all, I need t sub 1. Looks like 1 is the first term. So I need 1 minus r. What is r? See, r is 3, because we're going 3 times 3 times 3. So 1 minus 3 to the n, which is 10, all over 1 minus r, which is 1 minus 3 again. Now, there's no reason this should work, right? This doesn't make a ton of sense. But believe it or not, it works. All right, so if I plug all this in, got to do my parentheses. So parenthesis, 1 minus 3 exponent 10, end parenthesis, divided by -2. Wow, 29,524. I have no way of double checking if that's right, because these numbers are kind of huge. But you can sort of see how you get some really big numbers going. Keep multiplying by 10, or keep multiplying by 3 to get term after term after term. You can see you're getting some really big numbers. So 29,000, it's not unreasonable. If we had gotten 29 million, I'd be a little skeptical, but heck, I'm not even sure that would be that bad. All right, so infinite sum formula. What's going on with this? What we're saying is, you know what? That's supposed to be a little infinity right there. What's going on with this is we're saying you could actually take not only the sum of 10 terms or 15 terms, but the sum of infinity terms. How could that happen? Well, if you look at this sequence right here, see how they're getting smaller and smaller? So it's going 1/8, 1/16, 1/32. You actually imagine that having a reasonable sum. And actually, if you just think about this, it actually works out kind of nice. I picked this particular one because if you add it up in your head, you'll see that the sum is actually 2. Because you add 1 and 1/2, that's 1 1/2. 1 1/2 plus 1/4 is 1 3/4. And then your next terms give 1/8. Add 1 3/4 and 1/8, and you get 1 7/8. So the running total is going to be 1 7/8, then 1 15/16, and then 1 31 32. So you can see how we always have a full count. The numerator is always 1 smaller than the denominator. Eventually we're going to get to like 1 and, I don't know, 10,031 over 10,032 or something crazy. So it's just kind of, this thing is actually approaching 2, and it's going to equal 2. Let's see if the formula gives us that, though. So the sum of infinity terms is going to equal T1, which is 1, divided by 1 minus R, which in this case is 1/2. So 1 over 1/2, which is 2. So the magic works. Now if you want to see where this formula came from, and here's what I recommend for how to remember this formula for the test. This is the original S sub n formula we used on the previous page. This is the infinity one. So what's the difference? We've got a 1 minus R downstairs in both, and we've got our T sub 1 upstairs in both. The only difference is we have this 1 minus R to the n thing to worry about in the sum of n terms. Where infinity, that's not there. But why isn't it there? Well, R, if R is a fraction, now here's the burn. Your ratio between terms has to be less than 1. It could be plus or minus. That's why the absolute value is there, but it has to be less than 1. Our terms have to be getting smaller and smaller and smaller. So if R is a fraction, something less than 1, and you raise that to a really big number like, oh, I don't know, infinity, a fraction raised to a big exponent is pretty much 0. Like, think about if you raised 1/10 to the 100th power, you'd have 1 over a jillion, and that's pretty close to 0. So what they realized was, you know what? If you take the limit as n approaches a really big number like infinity, this term right here is going to go bye-bye. It's just going to become 0. And of course, once that's 0, you just have this 1 times t to the 1 upstairs. And of course, 1 you don't need to write, you just got t to the 1 upstairs. So that's where this infinity formula comes from. And the way to remember it is just think to yourself, you know what? That r to the n term goes bye-bye if we take n towards infinity. But here's the big burn. R has to be less than 1, like I just said. So let's look at a couple examples where they're going to try and burn you. Now, this does not work for arithmetic sequences. So the first burn a teacher could try and pull on you is to ask you for the infinite sum, but then give you an arithmetic sequence, like 2, 4, 6, 8. That just keeps getting bigger and bigger forever. So no way that would have an infinite sum. Here's another good burn one. This 1/2, 1/3, 1/4, 1/5. This has a special name. It's called the harmonic sequence, but it's not actually a geometric sequence. It looks like it's pretty systematic. I mean, the denominator keeps getting 1 bigger, but really the formula for this is 1 over n plus 1. It's not multiplying by something. It's not like 1/2 times something gives you 1/3 and times that same number gives you 1/4. It's just a totally random, it's organized, but it's not geometric, so this does not work. So the first burn they could use on you is to give you an arithmetic sequence. The next burn is to give you something that's neither arithmetic nor geometric, in which case there might be an infinite sum, but you don't know how to find it, and you won't have to find it in this chapter. And then finally, it could give you something that's growing. So if you look at this one, we're multiplying by 3 each time. So r equals 3. And that does not satisfy the criteria, that r be less than 1. So if you try and plug this in the formula, let's see what would happen. It wouldn't even tell you it's wrong. Yeah, so the trick is you just got to realize that r has to be less than 1, and if it's not, it's going to add up to infinity. And that would be pretty obvious. It's like 9, 27, 81. You can see these numbers are getting bigger and bigger and bigger, and obviously that's not going to add up to a small number the way the 1/2 plus 1/4 plus 1/8 plus 1/16 was obviously approaching 2. They're just going to get crazier and crazier as it explodes upwards. All right, so stick around for sigma notation. Very confusing to look at, but not so bad to execute.